I don't want to forget that. That would be a bummer. And actually, before I go into full screen mode, what I want to say is as follows, and it'll be in the email this week. I'll say it every day that we meet until then. But next Wednesday, the 21st, we're only doing Zoom class. Okay, I got to be in Billings for a 3-day long meeting. And I have no problem leaving my meeting and going and talking about math, because that'll actually be the best part of it all. So because I'm one of the leaders of faculty senate here, I have to go to all the board of regents meetings, which means sitting and listening to a bunch of things that I probably couldn't care less about. But every once in a while, there's a little thing. But anyway, so next Wednesday, we will still have class, but all I'm going to do is Zoom it. Okay. All right. And again, that'll be in the announcements, of course, as always. So, where we left off class last time is we were finding average rates of change, and we were just getting to some really cute ones if memory serves. But before I go and continue where I left off, I want to mention number one, that section 1.1 homework was due last Friday. My hope is everyone got it done. If not, you can still do it for practice, but it is too late to do it for a grade. And then section 1.2 in your online homework is due on Wednesday by midnight. As always, if you have questions as you're working through it, you can hit message instructor. If I'm able to answer it just by typing, I will. If I believe that the solution, so that you can understand it, involves more than just typing, will do. I am very happy to get a sheet of paper, write out the answers, take a picture and scan it and email that to you. So don't ever be shy about asking questions, okay? I don't live on my computer, thank goodness. But you know, I do check it multiple times, so that usually not past 7 at night if I can help it, just because I want some space, even though it's hard. But I'll get to your questions for sure. So I want to encourage that. The other thing that I want to do is I want to share my screen with you. And I am not seeing what I want to share, so give me just a second. There it is. Okay. And I want to be, good. I'm in your shoot. Oh, come on. One second. And normal, and then switch role to student. Okay. So I want to share my screen with this so that the people on Zoom can see it as well. All right. So this kind of came up last time. And so I wanted to make some things available to everybody. Okay. So one of the things that came up last time is a bit of uncertainty or fuzziness with some people on properties of exponents. Okay. I want to be able to provide you access to practice these things. And so what I've put on your class Moodle page under class activities and projects are as follows. I've put on properties of exponents. Ooh, I gotta post the solutions as well. Okay, so if you want to practice your properties of exponents, you can click on this thing, and there are numerous work through examples as well as examples that you can practice. Okay, this is not required. Okay, this is not part of your graded work, but I'm giving this to you as an opportunity for you to fill in gaps. Okay, if you want some extra practice in section 1.1 and section 1.2, what I would recommend you do is access these, and I also have solutions. Okay, any extra practice you're not required to do, but I want to give you opportunities to do these sorts of things. Okay, so if you look at this one, you know, notice that write a sentence explaining the meaning of this in the context of the problem. You know, determine what D of 0 is and write a sentence explaining it, et cetera, et cetera. So these kind of just go into a little more detail in terms of the interpretation. If you don't need help with this, you don't have to do this. Okay, I'm just providing it because you know, students in the past have sometimes asked for extra practice in a very harmless way, i.e. not graded. And so I like to provide that for you. So I have those on that class Moodle page if you want to do them, and I'm always happy to answer questions. Cool. Yeah, they're on there. The only one that wasn't on there was solution wise was the properties of exponent solutions. But just give me 30 seconds here. Oops. And I mean, they're all here. Now you'll be able to see the solutions. Yeah. It looks different from my view, from your view, because I already have everything front loaded if people want it. But I just don't make it visible until it's relevant. Okay, so yeah, there's solutions on there. Don't look at the solutions until you've tried to work it on your own. The problem with having solutions in front of your face is then you know what to work toward, and that always kind of steers the direction of your work. And unfortunately, in real life, we don't have the answers right in front of our face. Or maybe we do, we just don't see it. But now I'm getting philosophical. Questions? Now, before I jump in and talk about continue talking about section 1.3, this average rate of change business, does anyone have any questions on the online homework that you would like me to go through? Okay, well, as always, I'm going to start out class on Wednesday asking you the same question. Okay, so again, section 1.2 in your online homework is due Wednesday by midnight. So Wednesday in class is like an awesome time to do it. All right. So if memory serves, we found the average rate of change of like x squared plus 2x minus 1 from 0 to b. Wasn't that our, and what was the last example we did? Oh, I was going to promise you that one, right? Yeah. So I can do that example from x to x plus h, or I could take another function and we could do that one from x to x plus h. Does anyone have an opinion? Okay. I love when people have opinions. So what we want to do is find the average rate of change from x to x plus h. Now, as I mentioned to you on Friday, this isn't just some stupid math textbook question. This is for real, something that if you go on and you take calculus, you're going to have to do until you learn the shortcut. Okay? So, do you agree that when we want to find the average rate of change, what I need to do is find my function value at one, subtract off my function value at the other, and then divide by the difference between those inputs? Okay, remember we had that on Friday, f of b minus f of a divided by b minus a. And we saw that it didn't matter which order we went. Okay, now this looks funky, doesn't it? Yeah. Okay. Well, my denominator I can deal with right away. What is x plus h minus x? H. Hooray, that was cute. Okay, before I fill in all this mess in my numerator, I always do side work. I want to find what is f of x plus h. Okay, well, what does it mean to compute f of x plus h? Doesn't it mean everywhere where we see an x in our function f, we're going to plug in x plus h? Well, there's two places. So I have x plus h quantity squared plus 2 times x plus h minus 1. Are there questions how I plugged it in? I'm not done. I've got to like get rid of all parentheses and stuff. Okay. Now the fun begins. How do you do x plus h quantity squared? Good. That's x plus h times x plus h. Now, you can multiply this out by using the straight up distributive property, or a lot of people learned the FOIL method with this. They're equivalent. Doesn't matter which way you do it, they are exactly the same. Remember, the FOIL method only works when you have two terms in each of them. Okay. The one thing I don't want you to tell me is that x plus h quantity squared is x squared plus h squared. Okay, you can't bring your exponent in when you're adding or subtracting, only if you're multiplying or dividing. One of those pesky properties of exponents. All right, so have you all heard of FOIL? Okay. So first terms, what's x times x? X squared. Okay, deep question of the day. What is x times h? XH. What is h times x? HX or XH. I'm going to keep them in the same order. And finally, my last terms, what is h times h? H squared. Are there any like terms that I can combine here? Yeah, how many of these XHs do we have? We have 2 of them. You okay? Cool. So I've now multiplied out my first term, x squared plus 2xh plus h squared. What do I need to do with this 2 with my parentheses? Distribute. What do I get? Plus 2x plus 2h, and then I got this minus 1. You know what's a total bummer? Can't combine anything. So that's a long yuck, isn't it? All right, so the other term we need is f of x, but we already know what f of x is, don't we? It's just our function. So what I'm now going to do is plug these things into my formula. I need to take f of x plus h, which is this long shipwreck. And what do I need to do? I need to subtract my function. Notice I'm subtracting my entire function. So I put that entire second function in parentheses because we're going to need to distribute the negative sign. Now I know this looks terrible, awful, but you're going to have kind of a happy experience soon. Are there questions this far? Other than like, are you kidding me, Lauren? No, it's great to have those opinions. I love them. All right. So my next step is to distribute my negative sign throughout my parentheses. So first I got to write this whole yuck. And if I distribute my negative sign throughout my parentheses, can you tell me what I'm going to have? Minus x squared minus 2x plus 1, right? Distribute your negative sign throughout your parentheses. It changes the signs. All right. What cancels? Yeah, plus x squared minus x squared. What else cancels? These two x's cancel. Am I done canceling things? These ones cancel. 3 cheers. I'm being very sarcastic, but it's a gray Monday. So what do I have left in my numerator? I have 2xh plus h squared plus 2h. That looks better. All right, notice I have an h in each term in my numerator. Can't I factor it out? If I pull an h out of each term, what am I left with in my first term? 2x. If I have two h's here and I pulled one out, what do I have left? An h. And here, if I have 2h and I pulled out an h, what do I have left? 2, right? Do you agree if I distribute, I'd get 2xh plus h squared plus 2h? Okay, this is pulling out that common factor like what we were talking about on Friday. Now I've got an h times something in my numerator and by default an h times something in my denominator. What can I do to my h's? Bye-bye. So it's 2x plus h plus 2. Now, is this a huge thing in this class? No, but the whole point of being in a college algebra class is it prepares you to take calculus should you need to take calculus, okay? And this is something that you do in calculus. There's one more step. You would do something called take the limit as h approaches 0. And then you're left with 2x plus 2. And what you've then found is the derivative. Fortunately, there's shortcuts to do it because this sure is not eco-friendly. Do you want to see another one like this? Okay. I thought you'd be like, no, never again. Okay. So let's find the average rate of change. Let's do g of x is negative 3x squared minus 2 from x to x plus h. Then I'm actually going to show you a couple more funky ones just to make a point. So do you agree when you're asked to find the average rate of change, first thing you should do is set it up using the formula. You take the function value at one place minus the function value at the other, and then divide by the difference. All righty. Do you all agree in order to do anything up here, we need to know what g of x plus h is? Right? Don't we need to compute that? Okay. Well, it's negative 3x plus h squared minus 2. Now, if we could just walk away there, our lives would be a little bit simpler. Okay. What's my next step? Yep, we got to do the x plus h quantity squared, which we did. we saw before it's x squared plus 2xh plus h squared. There's no sense in reinventing the wheel, right? We did that right down here. You okay? Cool. Okay, what's my next step? Distribute -3. Someone else tell me, what do I get? -3x squared minus 6xh minus 3h squared minus 2. Do you all notice that I'm not just throwing this stuff in my equation right away? I do a lot of side work to set myself up. I highly recommend you do that. Okay, well, now I claim we can plug this whole razzmatazz in. G of x plus h is this mess. I'm going to subtract off g of x, which I have. And then again, those x's cancel and we're left with over h. What's my next step?
Put the negative in the last part there.
Beautiful. Let's get rid of those parentheses. So when I get rid of my parentheses by distributing my negative sign, what happens here? Plus 3x squared plus 2. And that leads us to be super duper happy because what cancels? The 2's cancel. Anything else? Yeah, these 3x squareds cancel. So we have -6xh minus 3h squared all over h. Can I simplify this a little bit more?
Yes.
Yeah, what can I do?
Take the H's out.
Yep, I can factor out an h again. Notice the steps follow each other. Now I can cancel those, so I'm left with -6x minus 3h. All right, there's one more I want to do because it's kind of yucky looking, but it's really good for us, like, you know, to stretch out and get used to practicing kind of yucky looking algebra. You ready? What if I want you to find the average rate of change of b of x equals 1 over x plus 3 on the interval from x to x plus h? Now, this is totally not a test question, okay? There's a very big difference between what's a homework question and what's a test question. Homework questions, you have time, you can ask help, you have multiple attempts, and seemingly you have as much time as you need to get it done within that week. Test questions are questions that are written so that you can solve them in a fairly short period of time. Okay, so there's a huge distinction between what I would put as a test question versus a homework question. Okay, this would be a waste of time for me to put on your test because you spend a lot of time on this, and that's not the point of the test. Unless it's one question test, that would be too hard. Okay, so do you agree that when we want to find the average rate of change, I want to find my function value at one minus my function value at the other divided by the difference between those? That's the part I can breathe with. And do you also agree that my denominator again is going to cancel to an H? All right. So what is B of X plus H? Well, that means everywhere where we see an X in my function B, what am I going to plug in? X plus H. So isn't that 1 over X plus H plus 3? Right? Where I had my X, I plugged in X plus H. Beware, when this step is easier, the rest of it comes back and bites you. Okay. And do you agree we know B of X is 1 over X plus 3? Are there questions how I got this? It looks deceptively simple, and that's why I want to make sure. Remember, what does it mean to compute B of 2? It means you plug 2 in here, right? So 2 plus 3, you'd get 1/5. If I wanted to find B of, sorry, if I wanted to find B of P, wouldn't it just be P plus 3? Right? Everywhere I see an X, I plug in a P. Now, everywhere where I see an X, I'm just plugging in X plus H. Well, plugging this in, do you agree in my numerator, I have B of X plus H minus B of X. And I already saw that my denominator simplified to an H. All right. So the reason why I wanted to do this particular example is because we haven't really talked about dealing with complex fractions and ways to simplify complex fractions. When I teach the 121 co-requisite class, the one that meets 5 days a week, we do these sorts of things front loaded, but I want to be sure that I show you these. Okay. So what does it mean to have a complex fraction? It means you have fractions within your fractions. I mean, one can translate that to, it means it looks like a rack. Okay. So there's a lot of different ways that you can go through and simplify complex fractions. I'm going to show you one such way. And we'll see this come up again in at the end of the semester when we do chapter 3, when we're dealing with rational functions. Okay. So all I'm doing right now is playing with some algebra. I'm wanting to make it so that this looks a little bit nicer. In other words, I want to get rid of my fractions within my fraction. Okay. Now, if this is kind of confusing, I'm going to walk through the steps, and I promise you we're going to do these reinforced again and again so that you get the hang of it, just as the semester goes. My quote unquote favorite way of making this look a little bit better is by looking at the fractions within my fraction, and in particular, looking at the denominators. Do you agree those are the 2 denominators within my fraction?
Yes.
Thanks. I love when people talk. So if I was going to get a common denominator, let's pretend I actually want to deal with this mess. If I was going to get a common denominator, do you agree a common denominator would just be this times this? Okay. Any questions there? So what I'm going to do is I'm going to take that common denominator and I'm going to multiply this entire quantity by it and divide this entire quantity by it. Okay. Do you agree I'm not changing the value of anything? Because if you multiply and divide by the same thing, that's the same thing as multiplying by 1. When you do these, don't multiply out your denominator, please let it be, okay? But don't we need to take this and distribute it throughout our numerator? Now I'm going to show every last step because I want to be sure you're all with me. So that means I have x plus 3 times x plus h plus 3 times my first term. And then I have my minus, and I have x plus 3 times x plus h plus 3 times my second term. And on my bottom, I'm just going to let it all be. Looking good, huh? Are you following the steps? Okay, we said a common denominator is multiplying these, so we multiply and divide by the common denominator. Now we got to distribute. Well, it's like saying this is over 1. And this is where life gets exciting. I promise you there's a silver lining here. What cancels in my first term? Well, what exists in both my numerator and denominator? X plus h plus 3. Bye-bye. And what cancels in my second term? The x plus 3's cancel, right? Because when you multiply two fractions, you multiply the numerators, multiply the denominators. All right. Do you agree in my first term, I'm left with x plus 3? Because everything else canceled. I have a subtraction sign. What am I left with in my second term? Oops, that's a 1. X plus h plus 3. And then I have this whole shipwreck. What would you suggest I do next? Good. I'm going to distribute my negative sign. So I have x plus 3 minus x minus h minus 3. What do I get to cancel in my numerator? My x's and my 3's. Am I done? One more step I can do. Look, I got an h up here and an h down here, and I'm multiplying. I think it's cute, but I'll put a question mark to leave that open for you. Whoa! So this is not a huge thing in this class, but these are the algebraic skills that we need to have down by the time we get on to our calculus class. So I'm planting the seeds right now. Okay? It's a really big seed. I know. But this is why we take the time and go through it. Okay. Well, now let's get on to the mellower part of this section. Right? Okay. We're going to talk about some things. And, you know, I really hesitate talking about some of these things right now, because honestly, I don't think that we really need to yet. But I want to kind of follow along with the book. But I will be very clear that this stuff that I'm mentioning right here won't be on your test. But also, before your first test, I'll give you a really good idea what to focus on. Okay, we got a bit before that. So what we're going to do is talk about graphical behavior. I always think it's funny to talk about the behavior of things. And what I'm going to draw is an example of some function. And this is my function f of x. Okay. And I just want to mention a few things about this function. Okay. So I'm giving you some terminology. Again, you don't have to have this memorized, but it is important for me to start planting these seeds. And these seeds are a little smaller than the previous one. So this is important terminology. Do you agree that we read graphs from left to right? Do you agree that as I'm going from left to right, right here, my function is increasing? And then I hang out for a second. And then what happens to my function? It's decreasing. And then I have this, what I call a turning point. What happens to my function? It's increasing. Okay. This point right here, where it changes from increasing to decreasing, I'm going to tell you it has a name. It's called a local maximum. In this area of my function, would you agree this is my maximum function value? Now, it's not my biggest function value because this thing shoots off to positive infinity, but locally in this neighborhood, this is my maximum. What do you think we're going to call this friend? Local minimum. They also can be called turning points. Okay, but notice a local maximum is when it changes from increasing to decreasing. And a local minimum is where your function goes from decreasing to increasing. You with me there? Cool. All right, so I call those local extrema. And then again, specifically the local max is the point where the graph changes from increasing to decreasing. And the local min is the point where the graph changes from decreasing to increasing. Okay, those are important terms in calculus. Now, formally, I claim we can say that a function is increasing if for a less than b, my function value at a is less than my function value at b. In other words, as my inputs are getting bigger, so are my function values. I claim when this happens, your average rate of change is positive. Why is my average rate of change positive if my function is increasing? Well, isn't f of b bigger than f of a? So my numerator is positive. And isn't b bigger than a? So my denominator is positive. Therefore, my average rate of change is positive. Does that make sense? And if you think about it, when you're finding your average rate of change, aren't you finding the slope of the line containing those points? So if this is my b or a and this is my b, if I was to find the slope of the line, I think you'd grant me that it's got a positive slope. Now, a function is decreasing if for A less than B, f of A is greater than f of B, right? In other words, as my x values are getting larger, my function values are getting smaller. Well, if this is the case, A is less than B, my denominator is positive. But if f of A is greater than f of B, what is the sign of my numerator? Negative. So when your function is decreasing, your average rate of change is negative. And again, if you're finding just the slope of the line containing those points and your function's decreasing, that slope is negative too. So that puts together a lot of really cute things with average rates of change and increasing and decreasing functions. Not a big thing, but a little seed planted. And I have 7 minutes to plant my next one. Okay. So the next thing is nothing that I would ever want to talk about until you take a calculus class. But I want to mention it here because I want to make sure I'm giving you the full experience, even though this doesn't even need to be said in this class. Okay. When you talk about the concavity of a graph, it discusses the shape. So I'm going to ask you maybe an online homework or two question on, concave up, concave down, but concavity is not on your test. So this discusses the shape of the graph. And what I'm going to do is I'm going to draw a couple of pictures and ask you to compare them. All right, we'll call this graph 1 and this graph 2. These two functions have something in common. I claim they're both increasing functions. Would you grant me that? As I'm moving from left to right, my function values are getting larger. Do you agree if it was pouring down rain, this would be the function I want to be under? Right? Because this kind of shelters me from the rain. Second. And whereas this puddles the rain. Okay. The shape of this graph we say is concave down. The shape of this graph we say is concave up. I write concave down as CD and concave up as CU. So both are increasing here, but one is shaped concave down and one is shaped concave up. You with me this far? Okay. Well, now what I'm going to do is compare these two graphs. Do you agree that both of these graphs are decreasing? As I'm moving from left to right, my function values are getting smaller. Would you agree the shapes are different? Okay, what would you say this one is? Concave up or concave down? Concave down, the water falls to the side. This is concave up. We're stuck in a puddle. So something that I want to note is that you can be increasing in concave down or decreasing in concave down. You can be increasing in concave up or decreasing in concave up. Okay. The way that you can tell whether or not, and this is much more formal than we need to do, but tying it to the average rate of change. Let's look at this. Okay. If I find the average rate of change of these 2 points, do you agree it's positive? Do you agree if I go find the average rate of change of these 2 points, it's also positive, but it's not as steep? Okay, so notice in graph 1, my average rates of change are decreasing as I'm moving over. Do you agree in graph 2? I got a positive average rate of change, but look, as I move over, aren't they getting really steep? Here, aren't my average rates of change increasing? So notice when it's concave up, my average rates of change are increasing as I move from left to right. That's separate than saying your function is increasing or decreasing. Let's talk about this here. Average rates of change, slightly negative, isn't it? But let's move over. Isn't it more negative here? So here, aren't my average rates of change decreasing because they're getting more negative? If my bank account's more negative, it's decreasing. And notice here, my average rates of change are really, really negative. And as I move over, they're still negative, but not as. So notice my average rates of change are increasing. So the moral of the story is you can tell increasing and decreasing by noting where your function's going up and down. But when your average rates of change are decreasing, your function is concave down. And when your average rates of change are increasing, your graph is concave up. Awesome. I got 1 more minute. Here is my John Travolta function. Isn't he increasing everywhere? Check this out. Isn't this part of my graph concave down and this part of my graph concave up? It can change within a graph. Oh boy. And where it changes, concavity, feel like I'm at the dentist, is called an inflection point. Nothing you need to know for this class, but if you go on and take calculus and you hear inflection point, you'll be like, oh yeah, I totally remember that. All right. Do you want to know something? Thanks. Guess what we just finished? 1.3. So what I'm going to do is share my screen. 1 second. I'm going to share my screen with our online homework. And go to section 1.3. Notice you have an entire week. I don't feel like I'm really piling it on. Okay. But if you do, I'm happy for you to give me your opinions. So what I will do is make this online assignment due a week from today. All righty, my friends. Have a great day.